So, hello everyone, welcome back to week 5 of our AI study jam. And here at GDG Ahlen, I'm excited to guide you throughout today's session where we are focusing on two crucial concepts in modern AI, foundational models and prompt engineering. This week is all about understanding the bedrock of any AI systems and learning how to efficiently communicate with them. Let's dive in. This event session will be recorded. So, in this session, we'll be exploring two incorporate topics. First, we'll demystify foundational models, the powerful engineer diving much of today's AI. We'll take a look at how these models, especially large language models or LLMs, have evolved. Then we'll shift gears to prompt engineering. This is the art and science of talking to AI, learning how to ask the right questions or, in AI terms, craft effective prompts. By the end of this week, you'll have a solid foundation of understanding and interacting with these advanced AI systems. So, let's start with foundational models. What exactly are they? In essence, these are general purpose AI models. The key here is general purpose. Unlike models designed for a very specific task, foundational models are trained on massive amounts of data. You think of the entire internet, books, code, and more. This broad training makes them incredibly versatile and adaptable. They are designed to be the foundation upon which we can build many different AI applications. Imagine them as pre-trained AI engines ready to be fine-tuned for a huge variety of tasks. To understand foundational models better, quickly look at the evolution of large language models, or LLMs. AI language processing started with simple statistical models and rule-based systems. Then came the machine learning era with models like LLMs and LSTMs that were better and processing sequences of text. Last year, Google introduced a family of foundational LLM programs and products, including Gemini, that represents the culmination of artificial intelligence research. The presented slide provides a detailed overview of Google's AI timeline. It highlights the most important developments in the rise of AI, culminating in the development of Gemini, a multimodal AI model. But the real game changer was the transformer architecture introduced in 2017. Transformer, with their attention mechanisms, allowed for parallel processing and much greater scalability. This led to the era of LLMs as we know them today. Think of milestones like BERT in 2018, which revolutionized understanding of text, and then the massive leap of GPT-3 in 2020, showcasing incredible generative ability. And now we are seeing even more advanced models like GPT-4 and Gemini, which are multimodal and even larger, pushing the boundaries of what AI can do with language. Let's explore some key examples of foundational models. And I want to start with Gemini, Google's most advanced foundational model. For those of you in the Google Developer Group, Gemini is particularly relevant as it represents Google's cutting-edge AI work. Gemini is designed from the ground up to be natively multimodal. This means it's not just about text. It can understand and generate across different types of information, including text, images, audio, video, and even code, all within the same model. A major focus with Gemini is on advanced reasoning capabilities, aiming to create AI that can think and solve problems more effectively. Next, we have BERT. BERT was a breakthrough in natural language understanding. It's like key innovation was bidirectional training, allowing it to grasp context from both directions in text, making it incredibly effective for search and understanding language nuances. And then there is the GPT series, the GPT-3, GPT-4, and now including Gemini in that lineage as well. These generative pre-trained transformers are known for their strengths in generating text and various forms of content, uh, fueled by their massive scale and parameter count. Before the rise of foundational models, we relied on traditional AI models. These models, like decision tree or early neural networks, were designed for very specific tasks. They required significant manual efforts in feature engineering and struggled to generalize to new or unseen data. For example, a model trained to classify images of cats wouldn't be able to classify images of dogs without significant retraining. The limitations of traditional models become apparent as the demand for versatile AI grows. The paradigm shift to foundational models was driven by the availability of large data sets and increased computational power. This allowed us to train models that could learn general purpose representations and be adapted to a wide range of tasks, moving away from task specific training. The journey towards foundational models in language began with early language models such as n-gram models. These models used statistical approaches to predict the next word based on the preceding words. While they were useful for simple tasks, they struggled to capture long-range dependencies and understand the deeper semantic meaning of text. For instance, they might predict the next two words based on the previous two or three words, but they couldn't understand the context of an entire paragraph. The advent of deep learning, particularly the transformer architecture, marked a significant turning point in AI. Transformers, with their attention mechanism, allowed models to focus on relevant parts of the input sequence, overcoming the limitation of recurrent neural networks. This led to major breakthroughs in natural language processing, enabling models to understand and generate text with unprecedented accuracy. The attention is all you need paper was the beginning of this revolution. The success of foundational models is closely tied to scale. Scaling laws show that model performance consistently improves, which increase model size and the amount of training data. This underscores the importance of having access to vast data sets and powerful compute resources such as GPUs and TPUs. The more data and the larger the model, the better the results. Fundamental models are characterized by their massive scale, often involving millions or billions of parameters. They are highly versatile, scalable, of performing a wide range of tasks, and exhibit few shot or zero shot learning, meaning they can adapt to new tasks with minimal or no examples. This makes them general purpose models capable of handling diverse applications. Multimodal modules represent a significant advancement integrating data from various sources like images, text, and audio. This enables applications in robotics where AI can understand and interact with the environment, and in specific research where models can analyze complex datasets from multiple models. The integration is crucial for creating more robust and versatile AI systems. Training these massive models is a complex and resource-intensive process. It requires a vast amount of computational power, often provided by specialized hardware like GPUs and TPUs. Data curation is another crucial aspect, ensuring the quality and diversity of the training data. Model optimization techniques are also essential to improve efficiently and reduce computation costs. This challenge highlights the complexity of developing and deploying foundational models. One of the most fascinating aspects of models is their emergent abilities. There are capabilities that arise as models scale, which are not explicitly programmed. Transfer learning is another crucial feature, allowing us to adapt pre-trained models to new tasks efficiently. Fine-tuning and prompt engineering are key techniques for task adaptation, enabling us to leverage the knowledge learned by these models in specific applications. In context learning is a very important emergent ability where the model learns from the information that is inside the prompt. As we develop and deploy these powerful models, we must address ethical consideration. Bias in training data can lead to biased models outputs, portraying social inequalities. Ensuring fairness and transparency is crucial to build trust in AI systems. We must also consider the broader societal impact of these technologies and, of course, develop guidelines for responsible AI development and deployment. Platforms like Vertex AI are making the foundational models accessible for real-world applications. They provide tools for deploying and customizing these models, offering APIs for seamless integration into various applications. Vertex AI also offers use case specific models, simplifying the process of leveraging these powerful tools in specific domains. This democratizes access to advanced AI, enabling developers to build innovative solutions. Vertex AI is a machine learning platform on Google Cloud Platform with a variety of generative AI foundational models that are accessible throughout an API. This is a platform for AI development and deployment. It allows developers to use pre-trained models like Gemini or train custom models with minimal effort. Key capabilities of Vertex AI are pre-trained models which are ready to use and vision models including generative capabilities. Automatically builds and deploy machine learning models, fine-tune models for specific business needs, integrated tools for deploying, monitoring, and managing AI at scale. And of course, Vertex AI simplifies the integration of generative AI into applications. It provides APIs and SDKs for various generative tasks, including text generation, summarization, and image generation. And now let's move into the exciting world of prompt engineering. Imagine you have this incredibly powerful foundational model, but how do you actually use it to get what you want? That's where prompt engineering comes in. Prompt engineering is both an art and a science. It's about designing effective prompts. They are essentially the instructions or questions you give to the AI. Think of them as your way of communicating with these complex models. The quality of your prompt is absolutely crucial. A well crafted prompt can unlock amazing capabilities, while a poorly written or might lead to irrelevant or unhelpful output. So, prompts are simply the instructions or questions we ask our AI assistant. Why should you care about prompt engineering? Well, it's incredibly important for several reasons. First, control. Prompts are how you control the behavior of these models. They guide what the model focuses on and how it generates its response. Secondly, electing desired outputs. If you want a specific kind of answer, a good prompt is essential. Vague prompts lead to vague results. Clear prompts lead to clear, relevant response. Efficiency is another factor. A well-designed prompt can help the model understand your request faster and more accurately, potentially saving computational resources and reducing the need for multiple attempts. And perhaps most excitingly, effective prompt engineering can unlock the full potential of these foundational models. By learning to prompt effectively, you can discover hidden capabilities and push the boundaries of what this AI system can do. The way we design prompts has a significant impact on how these models behave. Well-crafted prompts can help mitigate bias, ensuring that models generate fair and unbiased outputs. Effective prompts also enhance user experience, making it easier for users to interact with AI systems. This highlights the importance of mastering prompt engineering. Now let's delve into specific prompting strategies. The first one I'd like to stop and talk about is zero-shot prompting. This is perhaps the simplest form of prompting. In zero-shot prompting, you ask the model to perform a task without giving it any examples of what you want. You're essentially relying entirely on the model's pre-existing knowledge that it gained during its training. Zero-shot prompting works surprisingly well for mainly straightforward tasks, especially those that the model has likely encountered frequently in its training data. For example, we might ask the model to summarize a text without providing any example of summarize. Building on zero shot, we have few shot prompting. In few shot prompting, you provide the model with a small number of examples to demonstrate what you want. These examples are typically in the form of input-output pairs. Few-shot prompting is helpful when you need to guide the model towards a specific task, format, or style. especially for tasks that are more complex or nuanced than what zero-shot prompting can handle effectively. Let's look at an example of translation again, but this time using few-shot prompting. In the prompt, we provide a few examples of English sentences paired with the German translations. Then we give a new English sentence. The birds flew in the sky, and ask the model to complete the German translation. By seeing this example, the model learns the desired translation pattern and is better equipped to provide an accurate translation for the new input. A chain of thought prompting is a powerful technique that guides the model throughout intermediate reasoning steps. This helps the model break down complex problems into smaller, more manageable steps, improving its ability to solve reasoning intensive tasks. This method allows the AI to show its work and helps the user to understand the AI's reasoning. Really, this is a powerful strategy, particularly for complex reasoning tasks. The core idea is to encourage the model to explicitly show its reasoning process step by step before giving the final answer. You prompt the model to think step by step. This seamlessly simple instruction can dramatically improve performance on tasks that require multi-step reasoning, like math problems or logic puzzles. Chain of thought prompting can significantly boost the accuracy and reliability of model responses on complex tasks. To consistently create effective prompts, it's essential to follow a strategic approach. Providing context and relevant examples within your prompt is crucial for guiding the model towards the desired output. For instance, describe in detail the tasks that you want the model to perform. The task can be as simple as a step-by-step list of instructions or complex as mapping out a user's experience and mindset. The following prompt tells the model to summarize a block of text. The format of your prompt plays a significant role in how the model interprets your request. Prompt design has a lot of depth and nuance to it. We have a number of guides up on the website. This one is very comprehensive and could be a talk on its own, for example. If you need Gemini to perform multiple tasks, you might find it works better when you break the prompt up into small, atomic steps that are chained together. Adding context is also helpful. The model might be able to remember some facts, but they tend to work better when you give them all of the information they need to answer the question. And there are some model parameters you can tweak, things like temperature, top K, and top P. This guide explains all of these and how they affect the model. To enhance your prompt engineering skills, focus on setting clear goals, being specific in your instructions, iterating and experimenting with different phrases, and leveraging chain of thought prompting for complex tasks. These strategies will give you help unlock the full potential of foundational models. The benefits of prompt engineering are significant. Well-crafted prompts lead to improved model performance, reduced bias, increased control over model output, and enhance the overall user experience. This makes prompt engineering a crucial skill for anyone working with foundational models. To round out our discussion on prompt engineering techniques, let's emphasize the importance of being specific. This slide summarizes key aspects we've touched on throughout this third section. Remember, provide detailed instructions to remove any guesswork for the AI. Instead of broad requests, be precise, like asking for Flutter benefits in under 50 words, for example. Give context to guide the AI to relevant answers, such as asking about clean architecture specifically in Flutter. Use examples to show the AI the output format you want, like bullet points for summarize. And most important, iterate prompt engineering is about continuous refinement. By applying these techniques, clarity, context, examples, iterations, and specific strategies like zero shot, few shot, and chain of thoughts, you are well equipped to craft effective prompts and get the most out of foundational models. It's important to remember that prompt engineering is both an art and a science, as I mentioned at the start of the session. It's not just about randomly guessing prompts and hoping for the best. No, it requires a blend of creativity to come up with new approaches, but also a systematic approach to understand how models behave and apply the techniques we've discussed. Crucially, it's an iterative process. You will likely need to experiment, evaluate the model's responses, and then refine your prompt. Don't be afraid to try different things. See what works and continuously improve your prompts. Embrace experimentation. That's how you became a skilled prompt engineer. So, in conclusion, foundational models and prompt engineering are transforming the landscape of AI. Mastering prompt engineering is essential for unlocking the potential of these powerful models. Remember to continuously learn and experiment with different techniques. We encourage you to explore the resources provided, including Vertex AI and Google Cloud documentation, to further enhance your skills and stay up to date with the latest advancement in AI. So that brings us to the end of today's session. Thank you all for your participation. And of course, remember to submit post-event feedback form. It helps to improve and make future session even better. All materials used in this session I will share in our Discord channel and in comments under this video. Video was recorded and I'll share later on our YouTube channel. So once again, thank you for joining. We're looking forward to seeing you in our next session next Sunday. Until then, keep learning, experimenting, and building with AI. Take care.